Hi everyone. Today we'll be looking at hydrocarbons. So I'm gonna give you a brief explanation on molecular orbital hybridization and how it affects the geometry of hydrocarbons, and then we're gonna look at the impact of unsaturation on intermolecular forces. At the end of this experiment, you guys will have to carry out melting points of on compounds and solubility properties in them, and that would also explain the effect of unsaturation on intermolecular forces. Uh, so hydrocarbons are basically organic compounds that are made up of carbons and hydrogens. It's like the name says, hydrocarbons, just carbons and hydrogen. They have various uses in our daily life. For those of you who have cars, you have to buy gasoline in your car every day. Gasoline is, hydrocarbons. And hydrocarbons are very unique in the sense that they have the ability to generate a lot of energy when you burn them. So, for example, if you react an hydrocarbon with oxygen, because whenever you burn, you're burning in oxygen, the end result is CO2 and water and a ton of energy. That same energy that you use to run your car, to cook your food, to basically drives a lot of mechanical things that we generally do. And unfortunately, the end result is we end up releasing a lot of CO2 into the environment that leads to global warming. So it's really unfortunate, but uh, the importance of hydrocarbons in our daily life cannot be understated. So hydrocarbons, just like I said, are molecules that contain hydrogens and carbons. And whenever you have a molecule that generally has carbon and hydrogen, you automatically say it's an organic molecule. Okay. And the common examples are olive oil and margarine. Olive oil is a liquid, margarine is a solid, and there's a reason why that is so. Okay. And the reason why that's so, I'm going to explain to you guys later on, but it has to do with the number of double bonds and triple bonds that you have in your hydrocarbons. For example, if you look at margarine and olive oil, they all have very long hydrocarbon chain or tail. They have a very long hydrocarbon tail. And, that tail allows the molecule to pack in a specific way. The, the tighter the packing you have, the stronger the interaction you have between the molecules, the higher the melting point or the higher the boiling point. So in essence, what I'm trying to say is that the melting point or the boiling point of a molecule depends on how strong the intermolecular forces are between each of the molecules in the compound you're looking at. And it also has to do with the purity too. For example, if a compound has a lot of impurity, the melting point is not going to be as good because you have other things contaminating it. So the number of double bonds that you have in an organic compound, is known as the degree of unsaturation. And if you have one double bond in a compound, then it has 1 degree of unsaturation. If you have 2 double bonds in a compound, then it has 2 degrees of unsaturation. And unsaturation prevents your compounds from packing really well. I'm gonna explain this properly, as we move on. The saturation prevents your molecule to pack well because there are kinks in the molecule. It's not as linear, so you can't really pack as well. Okay, so so if you look at compound A, for example, compound A has a very long hydrocarbon chain. And if you have like 10 of this molecule, basically you can picture a scenario where you can, hold on, let me share another screen with you so you understand what I'm saying better. Okay, so if you have if you have a linear molecule like this, like so, and let's say let's call this molecule A, for example. Now, if you have this molecule in a bucket, now you just don't have one of this. You have billions and trillions of this in that bucket. And basically what happens is they can pack against one another like so. And as you can see, if you look at the hydrocarbon chain, there are no unsaturations, there are no double bonds there. So that allows each of the molecules to pack properly and then they can interact with one another. However, if you have a molecule that has a double bond somewhere in between, like so, what happens is it's going to be difficult for, because of the presence of this kink right here, it's going to be difficult for, all those molecules to interact properly. So the forces of interaction between molecule B is going to be weaker. It's going to be weaker than that of A. Okay. Okay. So yeah, so that's what I mean. So yeah, so there are basically three types of intermolecular forces of attraction between covalent molecules or organic compounds. Three main types. You have your London dispersion forces, you have your dipole-dipole interaction, and then you have your hydrogen bonding. Now, all organic molecules all have London dispersion forces, and one thing you should also know about those forces is they are the weakest form of, intermolecular forces you can have between organic molecules. The dipole interactions and the hydrogen bonding comes in when you start throwing in electronegative atoms into your molecule, like oxygens and nitrogens and chlorines and and lights. However, whenever you have just carbon or hydrogen, you only have London dispersion forces. And these forces are usually strong. They're usually strongest when you have, linear straight chain hydrocarbons. And just like I explained, in previous, previous shared screen, the interaction in a straight chain hydrocarbon is stronger than when you have branched system. And that's because in a straight chain system, you have tight packing between the molecules, and that allows for stronger interactions. Okay. However, in a branched system, you still have those interactions, but because you can't pack properly, the molecules can't pack properly, they can't interact properly, so they have weaker London dispersion forces. Okay. Orbital hybridization and molecular geometry. So basically in hydrocarbons or in carbons, generally, you can have three types of hybridization. You can have your sp3, you can have your sp2, and you can have your sp hybridization. So I'm sure you guys have looked at this in class, and I'm sure for those of you, most of you would have taken 101 or 103. They probably explained this well there. So in hybridization, basically what you're doing is you're mixing S and P orbitals to form hybrid orbitals that you can use for sigma bonding. In your sp3 carbon, you are mixing one S orbital with three P orbitals to form your sp3 hybridized orbitals. And whenever you have an sp3 hybridized carbon, that carbon is going to be bonded via a single bond to 4 different atoms. So you're looking at a carbon that has 4 bonds to 4 different atoms, and they are all sigma bonds. For your sp2 hybridization, you're basically mixing one S orbital with 2 P orbitals to form your sp2 hybridized orbital. to form 3 sp2 hybridized orbital. The extra p orbital will be used for pi bonding. Okay, so the extra p orbital is not hybridized. Instead, it's going to be used for pi bonding. So in your sp2 hybridized carbon, you basically have a carbon that's singly bonded to 3 different atoms, and then it's bonded via another bond to one of those atoms. So basically, you have a carbon that has a double bond to something, and then 2 bonds to 2 different atoms. Okay, so whenever you have 2 atoms bonded together, they can be bonded. They have to be bonded with at least 1 sigma bond, or at most 1 sigma bond, or at least 1 sigma bond. So whenever you have 2 atoms bonded together, it's usually 1 sigma bond. And if it's a double bond, then you have a sigma bond and a pi bond. And if it's a triple bond, then you have 1 sigma bond and 2 pi bonds. So 2 atoms can only be connected together via a sigma bond. If there are any extra bonds connecting them together, then they are all, pi bonds. So in your sp2 hybridized carbon, you have your carbon bonded to 3 different atoms, one of which is a double bond. So for those 2 atoms that have the double bond, one of them is a sigma bond, the other one is a pi bond. For your sp3 hybridized carbon, basically you have your carbon bonded to 2 atoms. For your sp hybridized carbon, you have your carbon bonded to 2 different atoms. One atom via a triple bond, and then the other one with a single bond. So it's a triple bond. Okay. Now for conjugated molecules, so basically conjugated hydrocarbons are compounds that have alternating double bonds. And what I mean by alternating double bonds are, when you look at the structure, you have a double bond, a single bond, a double bond, a single bond. So it's alternating. And that simply implies that, you have a conjugated system. There's also special conditions for conjugated molecules, known as aromaticity. So aromaticity confers a special degree of stability on some molecules, because of the way they are. Okay, and to determine whether a compound is aromatic or not, it follows a set of rules known as the Ockel rule, and this is something you guys are going to look at way into the semester. Okay, so I haven't spoken about that today. You guys are going to be carrying out experiments to test for solubility. You would also be carrying out experiment to test for melting point. Now, the solubility testing would build on the knowledge of your chromatography in your previous lab, because solubility has to do with like dissolving like. So you're going to be testing the solubilities of hydrocarbons, and you should intuitively know that hydrocarbons shouldn't be soluble in water, because water is very polar and hydrocarbons are not polar, because you basically have carbon and hydrogen, and they have similar electronegativity, so they are not usually polar. So you're going to be carrying out solubility tests on hydrocarbons. You have to follow through with the procedure one after the other, and then record your observations. For your hydrocarbon, for your melting point, hydrocarbon melting point, so basically you're going to be determining the melting point, and I think the melting point and the freezing point, the melting point and freezing point of your hydrocarbon. Okay, and to do that, you just have to follow, all the instructions you have written out in here. And I want to add that if you are given a compound, an hydrocarbon that's straight chain, you should know that the intermolecular forces of attraction between those molecules are going to be stronger. So you expect a higher melting point. And that's because whenever you're doing a melting point, you're converting your solid into a liquid. And to do that, you have to break intermolecular forces of attraction. attractions between those molecules. So if a molecule has stronger intermolecular forces of attraction, you expect the melting point to be higher. However, if a molecule has, a lot of, branched chains or a lot of double bonds, you know now that those molecules can't pack properly and their intermolecular forces of attraction will be, weaker. So you expect their melting point to be lower. So have that at the back of your mind while you're doing this experiment. Another thing I want you guys to look out for is when you set up your experiment, you want your thermometer to be sitting inside your solid, just as it's written here. Don't let your thermometer get suspended on top of your solid or hit the bottom of your test tube. You want it to be sitting suspended inside the solution. And also, when we say melting point, we are not actually looking at a value. Instead, we're looking at a range. So what I mean is you want to observe when the temperature, you have to watch your thermometer to watch for the point at which the temperature at which your solid starts melting, and then the temperature at which it stops melting. So at the end of the day, we expect you guys to report a range for your melting point. Like if I ask you if you are submitting your report, you shouldn't have results that would just say 73 degrees centigrade or 45 degrees centigrade. Instead, it should say 42 degrees centigrade to 45 degrees centigrade. It should be a range. Okay. The final point I would like to let you guys know is also that when you are transferring liquids with your pipette, you want to make sure that if you are reusing your pipette, make sure it's clean before transferring, subsequent liquids. Make sure it's clean in between transferring. So don't just, use the pipette to transfer a liquid and just dip it into another liquid to transfer. You risk contamination that way. Make sure you clean your pipette in between transferring. Well, good luck. Make sure if you have any problems, you can show up at office hours, and we'll be there to help you guys out. Thank you.